turbo engine running.
Absolute genius.
Get this.
Welcome.
This is the show where we bring you
Science.
What that essentially means is
discoveries,
Advances.
questions,
Research.
technology.
Unbelievable.
Without further ado,
This is The Naked Scientists.
Hello and welcome to The Naked Scientists, the show where we bring you the latest breakthroughs in science, technology and medicine. I'm Will Tingle. This week, the beginning of the universe and the search for extraterrestrial life, as we look at the technological marvel that is the James Webb Space Telescope.
And we have engine start. And liftoff.
Décollage.
James Webb begins a voyage back to the birth of the universe. Punching a hole through the clouds, 20 seconds into the...
Over the past 15 months, we've been treated to a new way of looking at the universe. Images of newly discovered galaxies, cosmic formations, and potentially habitable planets have been coming through faster and in better detail than ever before. All of that thanks to the James Webb Space Telescope. To give us a rundown of exactly what the JWST is, here's astronomy science communicator Rosemary Williams.
The James Webb Space Telescope is a groundbreaking, space-based observatory that was launched on Christmas Day of 2021. It is the most powerful and advanced space telescope ever built, designed to explore the universe in ways never before possible. It was designed to study the formation and evolution of galaxies, the birth of stars and planetary systems, the atmospheres of exoplanets, and potentially identify signs of habitability or even life on other worlds. And in the past 15 months, the JWST has been sending back incredible images of our universe and fundamentally changing how we understand our place in the cosmos. Unlike its predecessor Hubble that studied mostly visible light, JWST is primarily an infrared telescope, which makes it uniquely suited for studying objects and phenomena that emit infrared radiation, like distant galaxies, stars, and exoplanets. It orbits the Sun at the second Lagrange point, a point in space where gravity from the nearby Earth perfectly balances the gravitational pull of the distant but massive Sun. This point is just over 1 million miles from Earth, which allows it to avoid interference from our planet's atmosphere and stay cool, ensuring optimal infrared observations whilst using a small amount of fuel. But unlike with space systems like the International Space Station or the Hubble telescope, astronauts will not be able to repair or upgrade the JWST. This meant that everything needed to be perfect on launch. The concept of a telescope like the JWST was pitched in 1989, and preliminary discussions even placed it on the moon. But the telescope's development was far from smooth sailing, and the launch was delayed 8 times between 2018 and 2021. The project even survived a threatened cancellation in 2011 due to the skyrocketing costs associated with being the most advanced piece of observational hardware ever put into outer space. It weighs 6,500 kilograms, with giant eye-catching honeycomb-like mirrors that have become synonymous with the JWST. Each of these mirrors is 0.74 meters across, made of beryllium and coated in a layer of gold. The entire mirror system is made up of 18 of these hexagonal mirrors, carefully pieced together to form a larger mirror 6.5 meters in diameter, collecting and focusing 98% of the light it receives onto its suite of scientific instruments. The James Webb Space Telescope has already begun to shake up what we thought we knew about the universe and its origins, and is poised to continue making profound contributions to astronomy and astrophysics for many years to come.
Rosemary Williams. Now, before we can look at how this telescope is unlocking the history of the universe, we must first look at the history of the telescope itself. And what better way to do so than with a very special retrospective?
Now, we have a very special extra guest who's with us this week, and that's Dr. Matt Mountain. He's the director of the Space Telescope Science Institute, and he's been overseeing some of the groundbreaking work that's been done with the Hubble Space Telescope, as well as working on its successor, the James Webb Space Telescope.
In 2011, Dr. Matt Mountain, the then director of the Space Telescope Science Institute, came onto The Naked Scientist to talk about overseeing some of the development of the James Webb Space Telescope. Many hopeful predictions around time frame and budget were made. So how well did they stack up? Well, Matt is now president of the Association of Universities for Research in Astronomy, and he joins me now to look back at the JWST's development. Matt, thank you very much for coming back to speak with us. Let's start with the cost. In 2011, you were very honest and upfront about saying that the price tag had gone up from an estimated $4.5 billion to $9.3 billion. Did that then keep on budget?
No. Like all of these things, when you do one-offs, every time you think it's safe to go out, you discover something else. So one of the problems when you build this very complicated space telescope is, right, we make these incredibly lightweight, high precision optics that have to unfold 1 million miles from Earth. And then you have to fold it up and you have to have this sunshade wrapped around it. It's the size of a tennis court, but think of a tennis court made of 5 layers of space blanket. So you have to carefully fold up this space blanket, not to rip it. And you pack all this in. The real problem is you then have to put it on top of a rocket. And rockets are really violent things. They shake and they have lots of sound. And so to make sure the thing doesn't fall apart doing this, you test it. You put all this stuff together, and we have these big shakers. Northrop Grumman has one, NASA has one, and you shake the whole of this beautiful optical system, and there's lightweight sunshade and all the instruments. You shake the bejeebers out of it as though it was being launched. Unfortunately, during one of those shake tests, a dozen or so small nuts fell onto the floor in the shake room. And it turns out that, in fact, all of the hundreds of these small little bolts and nuts had not been installed properly and all had to be replaced. And that put at least 1.5 years delay and cost us an extra $800 million. So we had to go back to the US Congress and say, everybody promised not to do this again. We got a plan in place. We packed it up. But a result of that hearing, it was actually decided that, okay, at this stage of the project, you've managed to hold the budget for 4 or 5 years to this level. You can have this extra $800 million. But that's it, guys. Do not come back again.
You mentioned that this unfortunate development delayed launch by 18 months. Now, back in 2011, you were hoping to have the JWST launched by 2018. Obviously, you have the shaking incident, but also the COVID word will be floating around any plans that happened around 2020. Were these two factors the reasons for the delayed launch?
I have to say, full credit to the teams and everything. COVID had not such a huge delay. The biggest problem was this, trying to make sure that we had thought of everything, retesting everything. After we found these screws that fell out, there was this big push to go back and test everything, because there are 300 single point failures in this spacecraft. And we had to make sure every one would actually work. And so there's this methodical effort to go back and make sure we hadn't made any more mistakes in putting this thing together, that we actually understood where everything came from. It is amusing, yes, because as you say, when I spoke to you, when we wanted to launch this, my wife used to say to me, darling, when we first started this job, you're going to launch it next year, and you're still trying to launch it next year. He said, you're doing really well at your job. But it worked flawlessly because of all of that.
Exactly. And December 25th, it made it up into space. Now, I get nervous taking my camera on an aeroplane. I cannot imagine how tense it must have been strapping $10 billion worth of telescope with 300 single point failures onto a rocket. How do you get something so intricate up into space in one piece?
First of all, you have people looking over your shoulder as you pack this thing up. Everybody checks everything. We had even worked out how to make holes in the fairings so as all the air escaped as the rocket shot up through the atmosphere and got into the vacuum of space. We even made sure that the way the air escaped from all the folds of the sunshade would not rip the sunshade. All these things that we didn't know we'd have to worry about 5 or 6 years later. We even worried about what temperature the spacecraft would be at. And so we had to roll the Ariane as it was actually exiting the atmosphere, because the sun is sort of like a barbecue. We had to roll it round to make sure we actually got heat evenly distributed around it, so we didn't overheat some part of it and actually cause some damage to some of the multiple glued and then joints that we have on the back sunshades. It was a very, very complex launch process. And I have to say, Ariane did a superb job, because we had no course corrections. And it basically made it to L2, 1 million miles from here, with all of its fuel intact. So we actually have something like 20 years of fuel left. We had expected to use fuel on the way to actually correct it. We didn't. But of course, the problem is for all of us who had actually been working on this, unfortunately, the launch was only the first of holding one's breath. Because with the James Webb, launch is only the beginning of all the issues that we had to do. We then had to unfold it. We had to deploy this sunshade, not rip it. We had to unfold the mirror and make sure it was all working. And then we had to line all these mirror segments up to make it work as a single mirror, which means you had to line the mirrors up to less than a wavelength of light remotely, a million miles from Earth, where the telescope was cooling to roughly, minus 200 degrees centigrade.
After all that planning and all that stress, was there a singular moment where you and the team went, wow, this has all worked and worked perfectly?
I think everybody was sort of hugely relieved, mildly surprised, I think, that everything went so incredibly well. But I think that's a testament to all the problems we'd had previously, that we had to go back and retest, re-examine. And that paid off on the day. So when we actually deployed the spacecraft up, we got it out to L2, we saw the mirrors for the very first time, and then we managed to line all the mirrors up for the very first time. That very first image, we had this sort of hexagonal shaped stars. The mirrors began to line up and come into phase, as we call it. The background lit up with all these points. I remember looking at this image and all the engineers asking me, what are all those points in the background? Nobody was looking at this star anymore. They go, oh my goodness, is that the detector not working too well, Matt? Or is that this? It turns out those were galaxies. James Webb, in its alignment image, the whole sky was filled with galaxies. And that's when I realized this telescope was going to work incredibly well.
Matt Mountain, thank you very much. And I look forward to seeing how things are going in 2035. Now, the James Webb Space Telescope was launched with three main directives in mind: to see light from the early universe, to study the formation of new galaxies and cosmic bodies, and to look for signs of life on other planets. So, in the past year or so, what has it been seeing in regards to these things? Well, let's begin with a mystery surrounding the very start of our universe. The James Webb Telescope is powerful, so powerful it can look across the cosmos and see the light produced from the very earliest stars. You can age galaxies by looking at the photons, particles of light, that these galaxies are producing. When stars, and therefore the galaxies that they form in, are young, they produce photons with shorter wavelengths, which appear blue. So by measuring the ratio of short to long wavelength photons being emitted by a galaxy, you can measure its age. Young galaxies aren't as bright, nor are they as massive as older galaxies, as these things increase over time. But when Gochao Sun and his team at Northwestern University took a look at some of these earliest galaxies, they spotted a problem.
One of the biggest puzzles was that we found too many bright galaxies in those very early epochs. If you're thinking about a normal galaxy or typical galaxy, there's a pretty general mapping or correspondence between how bright they are and how massive they are. So if we take that general mapping that we build, then for those very bright galaxies, we would infer a pretty high mass. So that end up being in trouble with some of the very fundamental knowledge we have about the early universe.
Some early galaxies are too bright, seemingly too massive, to have formed in the short period of time that the universe had existed. Now, people studying the universe adhere to the standard cosmological model, the notion that the universe started with a big bang, went through a period of exponential inflation, and has been expanding ever since. But if galaxies can become this bright this quick, perhaps our understanding of the universe is wrong. Well, before we rip apart the fabric of reality, let's look for alternative explanations. And unfortunately for this program, early blame was pointed at the James Webb Space Telescope's equipment.
In terms of whether the exposure is saturated or something like that, I think astronomers, they of course did some very careful job, making sure this is not something that will contaminate or bias their measurement. But on a related note, there was indeed some calibration issue in the early analysis of the data. So that, of course, had led to some systematic offset in terms of the brightness or any other things that determine from the brightness. But that has been fixed, and the current data that we analyze and compare with models they have been corrected for this issue. So we think we are immune to those contamination or systematic uncertainties.
Thank goodness then, our technical marvel is not responsible. So is it then a fundamental shift in our knowledge of the universe? Well, Guoxiao and his team ran some simulations and have a different theory.
So I think the key factor here that is like central to our study is that in order for those early galaxies to be bright, they can either be really massive, or there's actually an alternative way of them to become very bright, which is that they can form stars in a highly like time variable manner. The rate of star formation can actually fluctuate very crazily over time. So you can end up with a very strong recent burst of star formation, meaning that you form a lot of stars than you would like normally expect in a fairly short amount of time. And that will temporarily boost the brightness of the galaxies without making the galaxy itself being like too massive or forming like too much stars.
So these periods of unusually high star production, dubbed bursty star formations, are instead what might be responsible for such unusual brightness at the beginning of the universe. Rest easy, everyone. The universe is still very much as we believe it to be. You're listening to The Naked Scientists with me, Will Tingle. Still to come, how likely is it for the James Webb Space Telescope to find signs of life in the next 25 years? But as we were just discussing, the JWST is helping to solve all kinds of cosmic mysteries, but there are still plenty of them out there, and very recently has come the discovery of a new cosmic formation. Jupiter Mass Binary Objects, or JUMBOs, are the latest thing to come out of images from the JWST. As the name suggests, these are binary, two objects orbiting one another in close proximity. They're too small to be stars, but also don't orbit a star like a conventional planet would. So what on Earth or in space is going on? I spoke to the University of Exeter's Matthew Bate.
The thing about the James Webb Space Telescope is it works in the infrared and also very high resolution. This was pointed at the Orion Nebula cluster, which will be very familiar to any amateur astronomer. And these jumbos, they're very young, so they're relatively hot because they've just recently formed. The assumption is that these jumbos are also around 1 million years old, but some of them still have temperatures below about 1,000 kelvins. It's like 700 degrees Celsius. And so these primarily in the infrared, which James Webb is perfectly designed to spot. And the surprising aspect is this about 42 objects that appear to be binary Jupiter mass objects. So several Jupiter mass planets orbiting around each other, but not in orbit around a star. And this has never been seen before.
They're being described as objects rather than, a star or a planet. What about them is making it so difficult for them to be classified?
So these come right at the boundary where they could form a little bit like stars form, but then they'd be extremely low mass compared to stars. Or they could form like planets, but then they're quite high mass compared to most planets, which means they potentially could form either way, and we don't really know which way they are forming. So stars, we believe, form in clouds of mostly hydrogen and helium gas with a bit of dust, a bit of heavy elements. These clouds, when they're dense enough, they collapse under their own gravity, get denser and denser, and eventually form an object, a protostar, which may initially only be a few Jupiter masses of material, but then it accumulates more and more gas from the surrounding cloud and grows to higher and higher masses. Below about 75 Jupiter masses, these objects are not massive enough to fuse hydrogen. So when they form, they're very hot, but then they just cool down because they don't have a hydrogen fusion power source. And so these are known as brown dwarfs. And when you get to below 13 Jupiter masses, then they have no fusion at all. So the other possibility, of course, is that they form like planets. So we believe planets form in disks of gas and dust surrounding a star. But the interesting thing about these jumbos is they're not orbiting stars. So if they formed as planets, they then would have had to be ejected from the star that they formed around. But they're also binaries. They're orbiting each other. So that means you'd have to eject to several Jupiter mass planets simultaneously and yet still have them bound together in a wide orbit.
So it seems putting all this together, what we know of them, our conventional way of categorizing things, well, it might be able to explain a freak event, but these are very common, seemingly.
Exactly right. So to form low mass brown dwarfs the same way as stars, I've worked a lot on theories where you might form a few objects, like 4, 5, 6 objects in a collapsing gas cloud, and they will interact with each other gravitationally, and maybe you can throw some of these out of the cloud when they still have just a few Jupiter masses of material, so they don't then accrete up to become a proper star. But how do you get binaries chucked out of the gas cloud? That's not very clear. If you had 1 or 2 of these binaries, you could say this is just a freak event, which, 2 objects happen to get thrown out about the same time. They were weakly bound together. But the issue is with these observations, they've spotted 42 of these objects in a cluster where there's around 400 free-floating Jupiter mass objects. And so this isn't a freak way of forming them. Whatever the mechanism is, it's forming quite large numbers of these.
Obviously, it's very early days, but would you like to speculate on any of the theories as to how they're forming then?
To be honest, I don't think any of our theories really explain this. Again, they might explain 1 or 2, they just don't explain how we've got so many of these in a single cluster. One of the interesting things now will be to use James Webb to look at other young star-forming regions and to see whether you see more of these jumbos in every young star-forming region that you look at, or whether this is unique to Orion. If it's unique to Orion, then it may have something to do with the fact that you've got massive stars there. So massive stars emit very strong radiation fields, and these can destroy the molecular clouds in which stars are forming. And so it's possible that in Orion, you had a whole lot of stars that were just about to form and collapsed to form very low mass objects that then would have gone on to accrete more material. But cloud was then overwhelmed by this radiation from the massive stars, blown away, and you just leave these low mass objects which don't have the opportunity to accrete to higher masses anymore. And again, why is it only objects with a few Jupiter masses? Why does this seem to be happening just around maybe 1 to 5 Jupiter masses? We don't really understand it, I think.
And as a final point, just to ease everyone's mind, we are talking about these unknown giant entities flying untethered through the galaxy. We're not expecting to see one anywhere near Earth soon.
Well, that's a good question. The older ones would be quite cold, and so they'll be hard to spot, right? Remember, the only reason we can see these with James Webb is that they're very young, and they still have temperatures of maybe 1,000 Kelvin. So they're emitting very strongly in the infrared. But these will cool quite quickly. And as they cool, they become much, much fainter. And so they're harder and harder to spot. And so if there are large numbers of these things around and they're quite old, they'd have to be quite close to us in order for infrared telescopes to spot them. So it will be interesting to try and work out how close you'd expect the closest of these to be. But there could be some hiding out there because they could be old and very faint, and we might not have detected them.
Matthew Bate, thank you very much. With all the talk of distant star systems and galaxies, the subject of habitable exoplanets and terrestrial life inevitably rears its head. And the JWST has been a huge contributor to this wave of planetary discoveries. Here to talk us through just how the James Webb is helping us look for signs of life and some of the most promising findings is space scientist and author Dr. David Whitehouse.
I think the most outrageous way is if it saw something strange in one of its image, what's called a technosignature, because there are ideas in science fiction that when civilizations get very old, are very accomplished, and they can do great things, they might start to rearrange a solar system. It has happened a few times in the past with other telescopes seeing strange things in the sky, but they've always been explained as natural phenomenon. But it's not breaking any rules of science or physics to suggest that someday some astronomer might look at some object, look at the data from some object and say, that looks pretty strange. Does that show any sign of intelligent interference? But that is the science fiction end of it. And no telescope is designed to do that. What the James Webb Telescope is designed to do exceptionally, exquisitely, brilliantly is to analyze light. It's got two spectrographs, which takes the light in various parts of the infrared spectrum, and it splits them into their component wavelengths. And every molecule has a spectral signature, methane, carbon dioxide. They're all identifiable in a spectra. So if you want to either look at a planet on its own, if it's sufficiently far away from its host star, and you can look at the light from it directly, you can then analyze that light. Or sometimes, as is often the case these days, you see a planet that moves in front of its star and causes the star to dip in brightness because it's obscuring some of the star's brightness. And by a fancy bit of footwork of analyzing the light when the planet is in front of the star, to the side of the star, and perhaps behind the star, you can actually pull out the light from the star that's traveling through the planet's atmosphere. And then you can look for these absorption lines, these spectral signatures. And that's been done a couple of times with James Webb with very interesting results.
When we single out all these molecules that we think might be sort of the giveaway as to signs of life, which molecules exactly are we looking for?
Well, we're looking for carbon dioxide, we're looking for methane, we're looking for oxygen, we're looking for ozone, we're looking nitrogen dioxide. They're fairly common molecules, but they are very good indicators of surface environments, and you can work out the physical characteristics of the surface of the planet. If you have other indications, I mean, for instance, there was a planet called K218b, which was recently very much in the news because they found evidence of methane water vapor, and some people suggested hints of a molecule called dimethyl sulfide, which is only produced by life on planet Earth. So that obviously caused a great deal of discussion because here you have a planet which has a molecule which on Earth is associated with life. But there had to be caveats with that because when you look at the analysis, the dimethyl sulfide spectral signature, its barcode, if you like, straddles several detectors. And if you don't individually calibrate those sensors, you might get the wrong impression. You might not get a good signal. If you don't calibrate them, you see the signal of dimethyl sulfide. When you did calibrate them properly, the signal was much, much less impressive. So although it's not been ruled out, it's certainly not been discovered, but it does indicate the power of James Webb.
One of the most striking things about the planet you mentioned, whose name escapes me briefly, is that it was, universally speaking, of course, fairly close to us. And it kind of implies that there's a lot out there that may even be able to harbour life that could be within travelling distance.
Well, yes, I mean, K218b was, I think, 124 light years away, fairly close. But there's an even better one called VHS 1256b, which is a Jupiter-sized object, but it's only 40 light years away. And we've got some fascinating observations of the atmosphere of this world. But the interesting thing is that it's thought that within about 50 light years of the Earth, there are 40, 45 exoplanets that we know of, and there are bound to be more yet to be discovered. But given the capabilities of the James Webb Space Telescope, the fineness it can read the barcode spectra from atmospheres of exoplanets, you're probably talking 50 light years away as being the farthest you could do this. So that shows there are candidate stars with planets, and interesting planets with interesting environments within reach.
And as a final bit of complete speculation, there have been some fairly outrageous claims recently that because of James Webb and all the capabilities we now have, we may well be less than 25 years away from finding life on another planet. What is your take on that?
Well, who knows is the answer to that. And it's nothing you can put your finger on it. We may discover life tomorrow. We may not discover life for decades. And that would tell us something very important about our universe. But I think every astronomer wants to make an observation, to look at some data and have that little sort of question mark in the head, which says, that's interesting. I wonder what that was. And when I was a professional full-time astronomer, we all had in the back of our minds, is this the observation? Are we going to be the famous astronomer to find life? Of course, nobody has been. But I think most astronomers have got that sort of excitement whenever they look at a new bit of data.
So take it from David Whitehouse. Never lose hope and always stay curious. And that's all we have time for this week. Next week, ahead of the clocks going back in the UK, we're asking where daylight saving time came from and what impact it has on the human body. The Naked Scientist comes to you from the University of Cambridge's Institute of Continuing Education. It's supported by Rolls-Royce. I'm Will Tinkle. Thanks for listening. And until next time, goodbye.